My name's David Byte. I'm a senior technology strategist here at SUSE on the IHV Alliances team.
Hey, I'm Matt Curley, and I'm a senior technologist at HPE.
So we're here today to talk about reference architectures on HPE hardware. And I'm really glad Matt's here because he is the expert. So I want to start off just real quick. We have a very long-standing relationship with HPE. This is something that goes back about 20 years, 15, 20 years. It's a huge, huge relationship. In June, we announced that HPE would sell and support SUSE Enterprise Storage on Apollo, ProLiant, and Cloudline systems. This is a fantastic announcement. Means that there's one throat to choke for our end users to purchase solutions, and that really gives a solid feel. HPE's been doing mission critical solutions for our customers for a long time around SAP and other parts of the business, so this is a natural extension. I think everyone has heard this by now. Micro Focus, the parent company of SUSE, has entered into an agreement to buy enterprise software from HPE. This is an agreement, it's not closed, there's a bunch of stuff going on for a long time. That's all I know, so don't ask, because I can't tell you anymore. But also at the same time of the announcement, HPE also announced that SUSE Linux Enterprise was the preferred Linux for HPE, and there was going to be further collaboration. We still don't know what all that means, but we got some preview in the keynote yesterday that there's a lot more going on than any of us are aware of, which is cool. So why a reference architecture? Matt, you want to talk to this one?
Yeah, sure. There's a lot. I mean, people can go in and say, sure, you can build this all together, but you really need some sort of place to start. And this is not just advertisement of the product, but it really is guidance for sizing deployment. We're going to lay out some stuff so people have a list and a nice focused sense to say, okay, these are my best practices. This is what I need to think about, and whether or not the problem I'm talking about right now is even going to fit with this particular solution. And then you are also going to get a selection of really appropriate hardware and use cases for this. Because I mean, if you're interested enough in Ceph, I mean, you know the story. It's really going to fit in certain areas, I mean, like cloud, et cetera, but you're not going to throw it in there and replace, like, let's say, SAN all flash arrays. I mean, it's just not there today. So what David really did a lot of hard work on this, take it to say, we're going to put this and actually put it through some paces. This is not just, we think this server could work for you, and you go and hope that that does succeed for you in a POC. So that's going to improve really the chance of success if you do get into a POC or some sort of RFP bid, and also a higher level of supportability because we've actually had exposure on both sides to the overall solution. And finally, that documented BOM there, that really is going to help with the conversation and tweaking it around, because I mean, when it gets into the details and you really understand what you're getting, not just, I'm getting a block of servers with some storage on them.
Thanks, man. So on the reference architecture with HPE, we've worked to produce reference architectures, specific implementation guides. The Apollo guide is live as of last week, finally. That took a long time, but it's there. And the reference architecture really is what matches that to business use cases, all right? It's the full picture of what it takes to solve a business problem. The implementation guide is a recipe that helps you get there very easily in a step-by-step guided manner. And we're providing both of those for the architectures we work with at HPE. So, Matt, I'm going to let you talk.
To the product line stuff? Yeah, absolutely. Yep. So, yeah, let's get the clicker because I'll probably be on this for a bit. All right, so the one you all know, ProLiant, and this is kind of the standard line of rack servers here. You're talking like DLs, MLs, things like that. Really here, it's about the DL380 and the DL360. So you're going to be able to fit in a standard rack, put these in colos, I mean, 2U and 1U form factors that a bunch of people have, but with our particular, obviously, HP brand of value. And when we say performance optimized, some of that is certainly for the overall use case. I mean, you'll probably have these in non-Ceph solutions, et cetera. But what you do have is the ability with the DL380 to really target it at some of the scale-out use cases. So you have a relatively small container for something to start with. You have that sort of, I already got exposure to it, and you can also be very flexible from the standpoint of I can put different cages in here and go small form factor, large form factor, or even build in blocks of NVMe in both. And between basically what you have in these two platforms, pretty much the same sort of processor. You've got your Broadwell V4s, you've got a fair amount of memory, 24 DIMMs, but really one is more focused that you can drive as a storage container. And of course, we also pull in things if you want that single pane and the BMC control that we've got up top there. So what we also have for people that are going larger scale, and this is primarily around density stories, is the Apollo series. So Apollo overall is around density, not just in storage, but there's also, we have the 2000, 6000, 8000 line for compute. This specifically gives building blocks sort of related to kind of the best use cases we can find in areas. And we've got stuff for also HPC. But in this particular case, we're going to start off with the 4200. Really what we see, this is a bridge server in for people to say, okay, I can put a 380 in and I like that platform, I like that form factor, but I need more storage density. I don't necessarily want huge big iron, but maybe I want to double what I could get in that same capacity. And so this has something, it's front loading, it's got a slide out sort of tray, and you can get 24 large form factor, or for some use cases, you can get fairly dense with small form factor storage. It really is very close to a 380 with that kind of more punch in the gig per rack unit. The 4510 is for people who really are going large, because what you've got in here, 60 or 68 large form factor drives in a 4U form factor, with all of them being hot pluggable. These do require the 4500 series a deeper rack, so that doesn't work for some people. It's fine for others that really can build up and go dense. But what you're looking at for this is that your building blocks are, we just came out with some of the 10 terabyte drive announcement stuff, so that's getting pretty close to 3/4 of a petabyte within one brick. So that's a lot of rebuild, that's a lot of capacity. If you're looking for, like a 10 petabyte sort of scale, this is very appropriate. If you want 200 terabytes of storage, you don't want this server. For the 4530, this is not necessarily an automatic fit use case for this, but this was more of a system that was designed around sort of a big data core spindle ratio, so that the whole synchronous thing for Hadoop where you have a certain number of cores that match up those drives. Where we have found it very effective though is, particularly if you're doing stuff for I/O with flash, et cetera, you may not want a huge building block. You don't want a lot of drives in one capacity for a failure domain thing, or maybe you just want to build like a wide erasure code with a large number of nodes or some other reason to have distributed out. So you can actually get within 4U 3 compute nodes, but a lot of large form factor storage. So it can sort of fit that middle ground for some of these use cases in more often a block use case than probably object. So really, while all these hardware platforms are different, the designs share a lot of commonalities in terms of availability. We've got the networking options, the redundancy, and you have this ability to fit in specifically the density for these scale-out solutions with RAM and CPU for Ceph, because it can get hungry with that, especially as you go deep. And you want to do through the reference design stuff, or?
Yeah.
Okay. Yeah. Talk a little bit to this, and you can pass it back when you want.
Yeah, we'll bounce back and forth on these a little bit. So the ProLiant reference design that we have is really designed for those smaller entry point clusters. As a customer, typically you're not wanting to start off with 2 petabytes of storage. Generally, you want to start off with a couple hundred terabytes maybe. And that really doesn't fit in the big platforms, but it fits in these. Also, these work really well when you're looking for a higher performance ratio out of your nodes. So by keeping the number of spindles low, you're able to deal with a lot more I/O without worrying about going across expanders and bus challenges and contention. That's really a great point to look at a server in this ratio, in this range of 12 drives in the chassis, or in a small form factor. 24.
Yeah, and you have back cages, and it's got a lot of options. But 12 is about a number to keep in mind.
Right. And another important factor, when you're looking at doing proof of concepts, a lot of times you don't want to shell out money for the POC hardware. You can repurpose because you probably have a stack of these sitting in your lab and in your data centers already that you can use. You may have to put some RAM in them, maybe put new drives, but you've got these things already there. So repurpose it's great. So when we look at the reference architecture, and there's a link, this presentation will be available online. You can also go onto our website, SUSE.com, go to /HPE, and there is a link to the reference architectures there. What we have is we have the OSD nodes and reference architecture built on DL380G9s, and the infrastructure nodes, the iSCSIs, the monitors, those are all built on the DL360. I really like the density that the platform gets, and you'll actually see some stuff done against this hardware this week. I'll kind of preview the Thursday stuff for you. This is an important piece right here, the redundant switch. So I know it's software defined and it's resilient and recovers. One of the things I really like about enterprise hardware, redundant power, redundant fans, give me everything I can to be redundant. Don't forget the network, please, please, please. But do it with hardware that is well tested and well understood. I would prefer when we talk about building a reference architecture, we don't do it with the absolute latest thing off the shelf, because guess what? We find problems sometimes in that latest driver or that latest hardware that's rolled out. So when we look at these switches that we're using from HPE, the DL300 series RA was done with 5740 series switches that are 10 gigabit. And what we did is we basically created a stack between the switches. HPE calls it a...
the IRF? Or?
Yeah, the IRF, thank you. HPE calls it IRF. So you create the IRF link, redundant IRF links, you stack it, and you can do LACP. Does everyone know what LACP is? I don't want to talk Greek to everybody. All right, so LACP, it's Link Aggregation Control Protocol. That doesn't mean a whole lot to you, but what it really means is you take 2 ports or more, we'll use 2, and you say these 2 ports look like 1. All right. Now, what's great about this is if one of the switches drops out, you still have 1 port. Your signaling rate just is slower, right? So it's 10 gigabit instead of 20. Make sense? That's keeping it simple. Anything you want to throw in on the 300 series stuff?
No, I think that's good.
All right. So the key design decisions here, really when we looked at the hardware and looked at how you should architect with it, these systems, really tend to be targeted towards VMware type environments. They work really well for that because they provide the performance. When you're building it, single socket. And the reason to go single socket, go more cores on a single socket at a higher clock rate, is the right thing to do. Stay off the QPI bus. There are things you can do to reduce the latency in Ceph. One of those is if you don't need to go multiprocessor, don't. Okay? It just makes things work faster in the back end. Now, I'm not talking 20% faster. I'm talking fractions of a percent. But they do matter because I'm a geek. Okay? Can't help it. I do like using the RAID controllers. I put the RAID controllers in. I put write-back caching turned on with a battery or a super cap on them. That's really important because what it does is it evens out the peaks and valleys from a throughput perspective, and it actually can increase the overall performance of the cluster, especially on reads. So if you were in Jan's session on CephFS yesterday, we may have seen some of that in his 4K read results where he suddenly got, he had 4K random writes doing, like 25 megabytes a second, but his 4K random reads were 4 gigabytes a second. So there was probably some read ahead going on there. Those controllers are really good at it. This one's really important. Write-intensive SSDs for the journals. If you're going to use journals, which you typically do in a performance case, and you're not using NVMe, and we'll talk about that in just a second. If you're going to use SSDs, use the write-intensive. Having the right bias in the hardware for how it deals with wear leveling and wearing out sectors in the chips is very important. If you don't use a write-intensive SSD, you could actually void the warranty on your hardware because you could write so much data over the course of a day that you've exceeded its writes per day. 2 SSDs for the operating system. Mirror them, please. I know it seems redundant, but it works. So walk through the config. The config that we did, 4 DL380 Gen 9s with 2 2.5-inch write-intensive SSDs, 1 mixed-use 3.5 for the OS. We were a little short on drives in what we did. Dual 10 gig E's. And you can see when we get down the monitor nodes, the RAM in these nodes is pretty high. I want to say we've got 64 or maybe 96 gigabytes in it. That's a little bit overkill depending on the size of the drives you use. In the case of using a 6 terabyte drive at a 1.5, you're going to want about 128 gigs of RAM in the system. We didn't have 6 terabyte drives, to say the least. I think that's all I want to cover. And if you have questions, please interrupt and ask the questions while we're going through. So what's it look like? So this is a built-out picture. I tried to get some photos actually of the hardware, but the way it was sitting in Provo, it wasn't all that pretty, so I didn't want to put it in here. So you've got your DL380s. Load them in the bottom of the rack. You know, this kind of, reminding you to keep it simple and think, because this is where all your weight is. You're also going to have a lot of heat coming out of these, so you may want to think about how you deal with the air distribution above and below your monitor nodes and then your top of rack switches. Ideal use case, virtualization storage. It's a smaller ratio of disks per node. Makes it give you the best performance possible. It works very well as a POC. And one of the things that our base of SEs tell us is that when customers are doing OpenStack, they tend to start relatively small in the 50, 60, 80 terabyte range of storage. And in that case, these are great systems to use. You can use them. We have some minimum recommendations in the way you deploy. We want at least 32 OSD devices out there. So you may end up with some extra storage capacity in the cluster when you're done, but this provides the best value for that.
All right, I'll take
so I want to let you talk to the Apollo, because I know you love it.
I love it.
Question on the reference architecture.
Yeah.
And maybe you'll get there. Okay, they're probably the same question for all of them. In that document, after you got the config, and by the way, the implementation guide really looks, that's really nice.
Thank you.
Do you have benchmarks in performance for each reference architecture in the document?
That's a great question, Dan. So the question was, do we have performance benchmarks for each architecture? And the answer is we don't have anything we've published to date in each architecture. What we have done is internally we are defining what that standard set of benchmarks we want to associate with each reference architecture is, and we're still trying to decide whether those get published or not. And the reason is that may not be something that our vendor partners want us to kick
even
out
from
there.
a competitive standpoint, there's no question that you're not the first person to mention this. And we would like to enable our relative field organizations to have that kind of information, because people come in, what do I need to buy? I want an SLA related to this.
But just to say it, right?
Yeah.
I mean, Red Hat Supermicro, Red Hat QCT have
Right.
Sure.
right? So
Yeah.
you get the question.
Well, and if nothing, even if they don't have something laid out necessarily, like you can get 30 ops for this, they have stuff that is organized in a specific way around this is an IOP platform, et cetera. So I can.
They have the form, and they have the form.
Yeah. So, but there's going to be some competitive stuff around that too. Customers will ask.
So from customers, let's say, okay, great, thank you. Just one follow-up. And let's say I have a bunch of customers who desperately want SUSE and HPE solutions, right?
Yes.
I'm just assuming then that if they're serious and they're working on it, at that point you can.
Yeah, so at that point we can look at the data we have, or the path that we're preferring to take from the SUSE side is we like to take these reference architectures and have an outside organization go through and do independent benchmarks of it. So if you look at the Apollo stuff, I don't know if I reference it here or not. We have an article that Storage Review did where they went through and they beat on it for several months and gave some really good solid benchmark information.
Yeah, I mean, certainly in terms of some of that, we can enable them to do investigations within a POC, but that's not necessarily a good first step. All right, yeah, no worries. So I'm going to talk about this from the standpoint of Apollo and those denser clusters. So really in a general sense, I mean, you'll talk to people and they may be interested, but they're not necessarily sure which are fit. So you will say, okay, like I said, there's a larger OpenStack sort of use case where you'll say, I want that 380 form factor, but more density and sort of mixing things in. The really sort of cheap and deep focus on object workloads and backup, direct-to-drive type stuff. And then we'll go off and say, okay, well, maybe for some of the things where you need more compute density, but just a little bit more in terms of drives than the 380, you can go with the 430. So we're really laying this out. All of those have kind of that setup. In terms of the same overall platform, there's the mix of, there's just sort of your smallest container, there's more drives, there's your most dense. You've got M.2, and that really helps out in some, we actually have the architecture in there, because the slot tax for some of this stuff, where you have to put the SSDs in, and you're looking to get that rack density, can really be a big deal to have to go to even the front 2.5-inch form factor drives. And so they're down there as the link for everything. So this is certainly got a fair amount of content in around what we did with the reference architecture.
Why is that David's favorite?
So that's a great question. So when you look at the price performance numbers, the 4200 just really cannot be beat. I mean, it's just right in the sweet spot.
And I'm going to say, I mean, from an HPE perspective, certainly this only fits a class of customer, and I think specifically for Ceph, really what he's talking about, this is really a great fit.
Absolutely.
They all have slightly different requirements in terms of what they need for hardware, but this is a great building block.
Yeah, if you've got a general requirement and for general purpose storage infrastructure, which Ceph is really, at that point where it's the right building block for that, I would recommend a 4200 every time.
Yeah. So this is kind of, I mean, this is not obviously down to the bomb. You're not getting all the SKUs out here, but this is a little more of a breakout of what actually was used. As you can see from the object perspective, when we talked about it, with all those OSDs, there's a fair amount of cores that needed to happen there. So you're way up in the 26.9 range, yeah.
So you'd be 2690?
It's 2690, what is it, 8 or 9? I can't remember.
2698, I think.
Yeah, I think it's, yeah. So basically what the kind of recommendation in here, you can go in and certainly be a little more precise if you know exactly what your workload is, but if you have like erasure coding and other things going on, you may need some overhead to make sure that you can take those spikes. And so also if you have flash involved, it's going to be a lot more, not in this case of course, but each OSD has kind of like, you're looking at saying, okay, I'm going to take a gigahertz for one of these spindles. Well, if I got 68 in a box, you've got a lot. And then you have to add extra overhead for all those other things I talked about. So
yeah.
They're working on some of that stuff. It is certainly a known thing, but one of the problems is when you create a networked architecture, right now, today, and we're actually getting to where a lot of the more recent work in Ceph has made this a bigger bottleneck than some other things. That can just going through all that packet processing can be a really big deal.
Yeah.
So we've got the PCI slots in here, and this is really mostly used up in these cases by getting this out of the box, your networking and your controllers for storage. The M.2 boot we talked about. This is mostly you have an extra back cage. Some people don't like hot aisle storage, but if you need most possible density, it's there. The RAID controllers, the battery back cache, they not only smooth stuff out, they're good for ephemeral commit stuff. I mean, you can absorb some writes. I mean, it's better even than flash if you've just got a little burst of random I.O. And redundant 40 or 410. I will say that, I mean, if you have this box, you might have a very cold storage use case. Really, we still tend to recommend at minimum 10 gig for rebuilds because you've got so much capacity. If you don't have that kind of pipe, rebuilds will take a long time. So then we also put together within the reference architecture the mixed stuff. And as you can see, the 4520 is not really the greatest fit, but it's actually got a dual domain thing, so it's more appropriate for something like Lustre. But here's the setup in terms of the number of SSDs and the number of spinners for that particular ratio. And then you pull it down. SSDs and spinners. You could go more aggressive with SSDs per se, but this is a mixed use workload, so you don't need to go and try to get as much performance squeeze as possible. And then there's the 4200, which is really saying, okay, again, I'm not putting as much journal as I could in here, but I'm getting good capacity out of the box, and I'm taking my back cage, and I'm putting all my journaling in there. And I don't remember where you've got in this, but NVMe is also a very good fit in this particular platform. So from here, we do have a little bit more of a beauty shot on this rack. Yeah. So we have the same thing, and the 4510s, you definitely have them in a rack. You want them at the bottom. The 4200s on top, and then I actually like doing this as well in terms of middle of the rack switching. It's not great if you want to hook together a huge pod, but it's really good for having shorter cabling for everything.
Right. So this is actually the rack that Storage Review went through and used and benchmarked against. The 3 monitors, DL360s, they're way overbuilt, and the reason for that is they're loaded up with SSDs, so I can do future storage testing there with all solid state all through the cluster. Now the guys from engineering are drooling on it even more, right? Again, the 2 flex fabric switches, they're in an IRF, redundant IRF, so there's an 80 gig uplink between them. And honestly, it's quite easy to configure and make work. I did turn jumbo frame on across the board on these, works fantastic. The serviceability of these systems is actually really good in the rack. Everything on the 4000 slides out the front pretty much. I mean, you've got a few things on the back, but most everything's on the front.
I mean, if you have stuff where you have really fragile cables, it can be a bit hinky, but you do need cable management on that. Everything, like I said, is hot pluggable.
Yeah. So it's a fantastic setup.
All right. So really what we're looking at here is if you're going to think about the use case you've got, you say, well, which one of these would apply? I said, deep object storage, video archives, certainly not like your streaming repository, your edge stuff. This is going to be kind of your origin server type storage, and of course, direct drive backup. The other boxes really are going to apply more mixed workloads. You're probably not going to drive all flash block like he was talking about. Right. If you're going to do that, you do it more out of a 360 or a 380. But larger OpenStack deployments are very efficient. More direct drive, perhaps in a warmer sort of thing, and HPC tiering, so like an HSM solution or something could definitely work from Lustre GPFS to Ceph. And wrapping it up. All right.
So we'll take questions in a minute, but really the thing I wanted to point out is, the choice is to pick the right systems for the right use, right? Don't think that 4510 is going to provide you really good performance storage for your virtual machine infrastructure. It might do okay for a little while, but once there's too many hosts, it's just really not built for that. The reason we do these reference architectures and the reason we do them with HPE are about enterprise reliability and enterprise support. In your data centers, you're used to having enterprise class storage. Enterprise class storage has characteristics that every storage admin knows. And the characteristics are all around being ultimately reliable, letting you sleep at night, stay home on the weekends. Those are the things we really expect out of those products. And Larry Morris back here used to design these arrays. He can tell you what you do when you're building these. HPE is the one-stop shop that provides this to our customers today. It's all the support, all the hardware, everything from the sale to the support to the consulting, HPE can provide it. So, any last words, Matt, before we had to take questions?
I think that really is one of the reasons I'm in particular here, and HPE in general is that we very much believe in this. I mean, what we've seen is these can be complicated systems, and we really needed a partner that could help us bring this to market in an effective way. And we get that it's not going to be a black box, but what SUSE brings to the table is the ability to get that enterprise reliability on the software side. And we've built this up so there really can be, as you said, one throat to choke and a solution that you can roll in. And that just makes it a lot easier to even consider for your use case.
Yeah. So any questions? Does anyone want to ask questions about the system buses and these things and how they're laid out to be optimal performance or anything? 'Cause Matt's got that. Questions? Yeah.
So do you tend to find, do you enable or disable hyper-threading on these things?
Hyper-threading?
Yeah.
So that's a great question. So initially, when I was building the systems, I was turning hyper-threading off in everything that I would do. And I would run my benchmarks and everything across that because it felt more stable. On looking what's happened in the upstream Ceph community, what's happened in the Linux kernel, what's happened, what Intel has actually done in the CPUs, really what we're finding is the hyper-threading provides some benefit, especially on the very, very dense systems. Yeah. So when you're looking at the 4510, turn the hyper-threading on for sure. Make use of it because you want every thread possible to be processed at the same time. If you're looking to eke every last bit of performance out of a 380, maybe you go with a more core dense processor and turn it off. But in general, just from a general practice, I would turn it on. You have any thoughts, Matt?
It's not going to, even in the case where it is going to benefit you, what I've seen is you're not like doubling your performance or anything by that. But it has gotten a lot more effective than it was earlier on in terms of probably being a better option. And yeah, when you have a lot of spindles, a lot of the best practices there are really saying, hey, I'm going to use that as efficiently as possible. In fact, you can find stuff where you set up where you're doing some of like the deep pinning, et cetera, where you really want some of that pachinko machine on the back end to kind of maybe share threads on the same core even. So you might want to have that enabled to make things more efficient.
Yeah. Other questions? Awesome. Well, we'll stay around for a little while.
Yeah.
And thank you for coming.
Thanks, guys.